Now we have reached a point in the chapter. We're going to look at a lot of application questions. It's not entirely new, but today we'll be looking at what we call power. Power we have seen before a bit in chapter 6, something to do with energy and power. Chapter 6, energy and power. We're going to look at a refresher about this whole idea, but just on circuits. Ooh, lots of good old stuff coming back. So first, we're going to recall and use the power equations. You remember the old one as P equals to IV, but actually, there's two other forms of this one, like cousins. There's 3 in total. So you need to know how to use them, and you also need to know this kind of a side story. This question has not come out in a while, but you need to know what resistance will give maximum power in a circuit. I also have a bonus part on this just because one of the facts has a mathematical proof to it, and it's kind of an extra thing lah, okay lah. So that will be an extra video after this one. But anyway, on to power. Previously, we looked at internal resistance, right? We say, in reality, you're gonna have energy loss and things like that. So what happened is you have, it's a recap of before, also important to help us look forward, energy supplied. That comes from your EMF here, this EMF thing. Okay, so you supply an energy, some of it is lost, but those lost and what is actually used inside, see this cute little light bulb here, uses some energy, and then there's some energy loss from internal resistance, it gets hot. So you will have some energy loss to internal resistance, plus the energy that is actually used in your circuit. So energy loss to big R, which is this one here, circuit. So energy loss to internal resistance, energy loss to circuit. This is basically an energy thing, lor. But if you divide everything by charge, so energy loss per unit charge, Q, energy loss per unit charge, energy loss per unit charge, what do we get? Well, if you kind of forgot a little bit what is energy divided by charge, it's good to maybe remember this. Remember we have work done, or change in energy, is the charge times potential difference. Aha! So that means energy, which is work done, divided by charge is the potential difference. Which means you can change this into V supply, potential supply, equals to energy loss due to internal resistance, so VR, plus energy loss due to circuit per unit charge, that will be VR, or otherwise what we call as terminal PD. Hey, this looks familiar. We've seen this before. It's just the previous video. So you recognize this in the form of EMF equals to the loss volts plus terminal PD, or the circuit resistance, the load of whatever is there, like, all add up together can be called VR or terminal PD. So this is how we come up with this idea. You can also link it to energy right here. And today we're going to look more at energy losses and energy spent, what is used, what is wasted. But a quick reminder, this light bulb right here is losing energy or using energy because it's transforming it as light, as heat. Bulbs get hot and other stuff, but these are the two main ones. Anyway, let's look at power electrical energy after we have connected that from internal resistance. So before this, you have seen this picture maybe kind of before. This is our good old Coulomb train model. You have a battery supplying energy. See these gold little nuggets here? Ooh, nice nuggets. Goes past a light bulb. And then, some energy is used up already. So you see the gold color is a little bit lesser. That means some energy is used, go past another one, use up even more, and then you must return empty. So potential drop is all done across the two bulbs here. So how do you think of energy in this case? Well, we already know a formula to think about it. We have our good old work done equals to charge, HQ, times the potential difference across 2 points. So, for example, this V here, okay? How much energy change is there when you take this charge from this point, move to this point? That is how much energy is used already, okay? There are also other ways we can write this. Another way you will see this very often, very handy here, is the change in energy. Sometimes you just say E equals to QV. But we're like QV, Q equals to IT, right? Can we just plug in Q equals to IT? Sure, let's expand it. Because oftentimes we won't see Q in circuits. We'll see current, ampere, resistance, ohm. So Q equals IT, so I have ITV. Let me rearrange it to something a little bit more easy to remember. E equals to VIT. EVIT. That is one way people use to calculate the energy spent by a component in a circuit. For example, this light bulb here will be spending some energy. I don't know how many joules, 48 joules maybe. But however you calculate it, that will be your E equals to potential difference before the bulb and after the bulb. That will tell you like how much drop and energy is there. Current will tell you how many of this trolley is going past, how many charges are going past this bulb. And then time will tell you how long you turn on your bulb. 3 hours, 2 hours, 1 hour. That will tell you how much energy is being spent. So all these three ideas come together to tell you how much energy there is, and this in units of joules. Good old energy. Okay, so now you have your work done stuff, and you also have this E equals to V. Okay, so that's the idea about energy. But what about power? Do you remember how we deal with power? It's a quick recap. So power can be measured as a current flowing through a component times the potential across that component. So if we have this light bulb, let's look at the second light bulb now. What is the power transformed by this light bulb? Well, you could say there's a current flowing through it. Let me redraw that. So light bulb, current flowing in, that's I. V here will be the potential drop between here and here. If you measure with the voltmeter, there will be a potential drop, and that's the V that we're looking at. And that corresponds to how much power is dissipated or power transformed. If you're wondering, Miss, how different is power from energy? Well, power is just energy over time, change in energy over time. So yeah, the only difference is time, lor. Okay, so if I do PIV, you can actually link both of it, lah. Okay, so where do you get this PIV from? Well, let's go through step by step. I'm going to show you where it comes from, because you'll be using it so much, but like where it comes from. Okay, so power is a change in energy over time. Electricity become light. Okay, change in energy. Change in energy, we have just looked at it up here. This work done is change in energy. That is our QV over T. Okay, and QV, we know over here already, we can plug Q equals to IT, and that will give us V IT over T. T and T can cancel, so T and T is gone. So all that's left is V and I, which I write IV. And that is where you get your P equals IV from. It's actually it all comes back to our mother equation. Work done is Q times V. That's coming from the definition of potential difference also. Remember from an earlier video how we define potential difference? Okay, so this is where it comes from, this P equals to IV thingy. There are also a few cousins that you need to know, the cousins of the PIV. Okay, there are many forms. So the other ways you can calculate power, other power equations, you have P equals IV, but also know that you have, this is what we call Ohm's law, V equals to IR. And you can plug in the Ohm's law to get rid of a number of things. For example, if I plug in V, then I will get I square R. Oh, that means now you can relate the current I to the resistance R of the component, in this case a light bulb, and you can still find the power dissipated, power transform, which is energy transformed per unit time. There's one more. What if we get rid of the I? Okay, so I want to sub out I, right? So I will be V over R. So then I'll get V squared over R. It also can calculate power, but this time you use V and R only. So this is super, super useful because now no matter what information you have, you can play around with it and see which power equation you want to use, all based on the same thing. Okay, so let's look at before we look at that, wait, I want to give you a quick heads up. In a circuit, right, if you have something like this, a battery, a variable resistor, this is a heads up for the bonus one that I'll do later. This variable resistor means you can change your R. Also, this one should have EMF inside and then the internal resistance. So as you change your R, the power that you dissipate will be different. The maximum power that your variable resistor here can dissipate, means like throw out, the maximum power is when your total circuit resistance, total circuit R, equals to your internal resistance. Internal R, this R. This is a fact you want to remember. Questions have not asked this for quite some while, but just in case it come out, I just want to let you know. So yeah, if this R match the small r inside there, then the maximum power will be thrown out by the resistor. And FYI, there's also a graph that looks like that. Dun dun. So if you plot a graph of power dissipated by this variable resistor against the total resistance of the circuit, which is this one, you get a very funny looking graph one actually. It's going to look something like this. It will increase at first, and then it will start to decrease and then go down like a mountain. And this maximum here is where your R is also equal to your small r. This is where your max power is. Now, if you're curious, like, Miss, why are you talking about this so random one? Well, I'm giving you a heads up so that you're ready to solve some of the questions that may come your way. Don't worry, there'll also be a bonus video after this one so you can get a good inside look on why this fact is true. Why total R must equal small r, then you get maximum power. Okay, we'll figure that out later. But this is just FYI, okay? So let's look at some equations or some questions that will get us practicing on this idea of power. First practice one's kind of more on the straight side, it's on page 25. Yeah, sure. Let's look at this one. How do you think of power and energy in electricity? So the charge that electric battery can deliver is specified in ampere hours. Why are they telling us this? Okay, sure. We'll write down ampere times hour, so IT. Oh, charge! Hey, I know this. Q equals to IT. Okay, good to know. So a battery of 40 ampere hours can supply 0.2 amp for 200 hours. This is just a FYI example for them to show you. So 40 ampere hours fully charged, I, and this is T. So you try to multiply I and T, 0.2 times 200. That gives you 40. Okay, good to know. Then they ask you, what is the maximum energy, E, that a fully charged, 12 volt, 40 ampere hours, so ampere hour is your IT, that a battery can supply. How would you solve this one? This is a fun one to do because if you know how to calculate this, I'll show you very fun later. You can calculate for your power bank if you have one. Anyway, let's see. What can we do with this? Well, this kind of looks familiar. EVIT. Hey, we know EVIT. That is how we can calculate the energy that your battery can supply at a certain voltage, with a certain current and time. So IT, they already give us ampere hours. So here, there's something I need to warn you about. But I'm going to write out the thing first. So 12, you say, yay, 12 volts. IT is 40 so 12 times 40 lah. Then we're done, we can calculate everything. Hey, wait. You try this and see, you see got answer or not? You realize that Something's not quite right, but it looks correct. Oh, what is missing? You need to check the units. Bro, this energy is in joules, so all this got to be in SI units. So this 12 is in volts. This 40, what's the unit of this thing? Ampere hour, all right, so it's AH. Ampere hour. Hour is not SI, we want it in seconds. This is in AH. So great. Okay, so we need to convert hours to seconds. So 1 hour is 3,600 seconds. So that will be a conversion factor there to help convert it to, what you call this? Convert it to seconds, right? All right. If you're wondering, Miss, how about the units? Well, if I write out the whole thing properly, 3600 seconds is 1 hour. So the hour and this H will cancel out. So all that's left is seconds. Okay, good. Now SI unit. Now I can calculate. So must be very careful when you do this calculation. If it looks too easy, you kind of want to pause and check and see whether your units are correct or not. So 1.728 times 10 to the 6 is what I get for this thing in joules, right? Oh, they kind of took away the prefix. So, okay, 1.728 times 10 to the 6 closest will be megajoules. So that will be C in this case. If you have a power bank, go and take a look at it. How you know the power bank got power or not? How you know the power? What's the energy that your power bank's going to supply? Usually power banks will have some MAH on it if you look at the number there. For example, mine here is about 10400. I cannot see. MAH. And it can supply a charge. It can charge my phone at 3.6 volts. Which is good for my small phone. If it's any higher, they'll be for tablet or laptop already. So this is basically what we just did here. You can calculate the energy that your power bank can supply, how long it will supply, how many hours, blah, 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 etc. Fun stuff. Very relevant also, ampere hours. Okay, but let's look at another example of more on power and maximum energy now. This is on page 19. So page 19, this is, what is this called? Not page 19, sorry, wrong page. Page 44. This is from MJ18 P11. So MJ18 P11. Oh yes. Okay. So here is a good practice on how you can use the power equations. There are a few of them. Try to recognize which one you need to use here. Here you have two lamps, two circuits. Now we come to circuits already. This one, first one got a current, second one got a current. Okay, good to know. What is the ratio? They ask you ratio. So whenever they ask you to do ratio related question, you find this one separately, you find this one separately, and then you divide both. That's the easiest way to do it. Okay? So let's see, what shall we use? Power, ratio of power. What do we have here? We have I, the current. We have the resistance R. So you need to use the power equation that has I and R in it. Which variation is it? Go and check. Not PIV anymore. You don't know the... You could find the potential difference and then do that, but that's extra work. Why not just do it all in one step? So the one you want to use is P equals I square R. That is it. So I square 0.5, R is 9.6. Then you should get about 2.4 watts. I calculate this one already. Then you do the other one separately. This is for PX. Then you have PY, also I square R. So I is 3 amps. R is 1.2 ohm. Write the unit. Okay. So 3 square, 1.2, 10.8 watts. Then to find the ratio, all you need to do is divide both of them. So the ratio of PX over PY is 2.4 divided by 10.8. That will give you 0.2222222222. Then you look, 0.222 here. Done. So that's your ratio of power. Ta-da! So this one is just a reminder. This is one of the variation. You have P equals to IV, P equals to V square over R, P equals to I square over R. It's helpful if you memorize it straight away so you know, this is one used here, this one used there. So you don't have, it minimizes your calculations. Next one, let's look at something in a circuit with internal resistance now. Oh. On page 19, you have this example where it's kind of like a puzzle. You have to figure out what piece of information you have, what equation to use, when to use what. This one, I want you to pause the video and try it first, because we have seen this internal resistance thing before in the previous video. But how do you solve it when there's energy involved? I mean, yeah, pause the video, give yourself time to try figure this one out. Okie dokie, let's look at this puzzle. A battery with constant internal resistance, good to know it's constant, is connected to a resistor of resistance 250 ohm, as shown. The current in the resistor is 40 milliamps. Okay, so I'm going to label this thing because it's going to be a lot of information later. So 40 milliamps. Sounds about right for a battery circuit, usually about milliamp scale. For a time of 60 seconds. Okay, so this whole thing is running for 60 seconds. That affects how much energy is being thrown out. During this time, 6 joule of energy is lost in internal resistance. So here, because of the R, you can say, oh, energy is lost as probably heat, 6 joules. What are the energies applied to external resistor? So what's the energy coming out here? The E. During this 60 seconds and the EMF of the battery. So you need to find what is your EMF as well. Wow, it's got a lot of stuff to find. How do you start? Let's start with the energy first. Energy coming out of this, energy supplied to the external resistor. Well, if you see energy, probably the first thing you think of is the EVIT, right? You'll be like, oh, E equals to VIT. There's just one little problem here. We know current, yes. We know time, but what is V? You could find V. Yeah, that's one way to do it. How about that? We can try that. You could say, you could plug in Ohm's law in this equation and no need to use V, but okay, let's find V. V equals to I times R. So 40 MA times 250. 10 volts. That means the potential drop across this one here is 10 volts. From here to here. That's a PD drop. Actually, another better way to write it is kind of just like this. Here to here, 10 volt. Okay. Then you can find, you got a V already, no? Okay, this one actually, there's many ways to do it. This is just one of the ways. So 10 times 40 milliamps, milli, don't forget to convert that, and 60 seconds. So then you have 10, 40 times 10 negative 3, and 60. 24 joules of energy. Sure, that is correct. So these two are out. Also, there is another way to do this. Some may prefer that over the other. If you want to use power equation, that's pretty much the same thing. You say, oh, P equals to I square R. Because I know I know R. Can use this, I miss? Can. It's basically the same thing. The EV and the power equation is just related by time only. Because if you have P, that is basically energy over time equals to I square R, which is the same thing as your EV there. So E equals to I square R is same as IV. So you do 40 milliamps squared times the resistance times the time. You will also get 24 joules. Same thing. Different ways as long as you get to the same place. Now we've got the energy dissipated. So energy is coming out here as heat, 24 joules in 60 seconds. And that is calculated from the potential drop of 10 volts with a 40 milliamp going through that. Okay, sure. How about the EMF? How to find? What methods do you try to find this fella? Well, one of the ways is to just find, you already know this potential drop, right? What if you can find this potential drop because of the internal resistance? Then we can find E already, ma. Okay, so how to find this one? Is there a way to find that? We only know that 6 joule is dissipated. Oh, wait, that's a hint. You know the energy dissipated from this internal resistance part is, let me put this small r to not confuse it with the other one here. Oh my goodness, I should put big R here. Okay, so when we have VIT, right? We know ER is 6 joules. We don't know what's VR. We're trying to find that. We know the current is 40 milliamps. Go here, milliamp, 40 milliamps. Still the same thing. So let's put 40 milli. And we know time, right? 60 seconds. So we can find the potential drop across that internal resistance bit, which is, let me divide it real quick, 2.5. Okay, 2.5 volts. Now, if you get overexcited and you say, oh, 2.5, so the answer is 2.5, and no. This is only VR. You need to remember that how does E, VR, and this resistors V relate? How do they relate again? Think back your internal resistance thing. E equals to the total potential drop across your circuit plus potential drop across the small little internal resistance there. Okay, so we can do this. 10 volts plus 2.5 volts gives us 12.5 volts. Ta-da! And like that, you have found your EMF of the circuit. If you have another way to do it, sure. As long as you know what you're doing and you can get there. So you realize how it's a lot of listing information and see what equation to use when. Because there's so many things to use now. You're like, huh? Each one got many forms. Actually, the E equals to V also got many forms one. I square RT and things like that. You just sub in Ohm's law, all three will come out. Okay, so practice a lot of questions like this, how to interpret and analyze what info you have, what you don't have. Here's a weird one that I decide to throw into the bunch of examples because I think this one has appeared more than once already. So like, they seem to like this one a lot. So anyway, this is a weird one because have you ever seen this kind of square graph before? What is that? At 100 ohms resistor, conduct a current with changing direction. What is this? Well, technically we're going to learn more of changing direction in A2. This is what we call AC circuits, alternating current. That's what your house supply usually use. But basically, what does a negative current mean? If you have a circuit like, let's say you have a circuit connect to a power supply, connect to a resistor. It could be something like this. When it's current positive, it's flowing like that, clockwise. Then, suddenly when current negative, then it flow anti-clockwise. So each time it will go clockwise, anti-clockwise, clockwise, anti-clockwise. Every 1 millisecond, it changes direction. That's just what I mean. That's what negative means. Okay? So how are we going to find the mean power here? Mean also means average, by the way. How to find the average power? Here's a trick you want to keep in mind when you see alternating graphs like this. If you want to find the mean power, you need to find each section separately. So we're like, what does that mean? Okay. When its current is 2 amps here, what is the power dissipated? Well, here the thing of power is, we have I, we have R, I square R. So 2 square times 100, that is 400, I think. Yep, 400. So when it's here, that's 400 watt. Okay? And then when the current is -1, then the power you dissipate here will be -1. Actually, the negative don't need to put inside there one. It's just FYI. So here will be also 100 ohms. That will just be 100 one, 100 watts. Here I should write 400 watts. So 100 watts. So if you want to find the mean now, what you could do is you take the average of both power when it's in the highest positive and lowest negative. So here you take average power, that will be 400 plus 100 divided by 2. 400 plus 100 divided by 250 lor. So here you can say 250 is the mean power when it is switching up and down, up and down, up and down, up and down. But it will hover around 250. Okay, the middle is somewhere at 250 watts in this case. Yeah, this is a weird question. You're like, huh? Why suddenly got graph like this one? Just FYI, if you see a graph like this, current against time, and then there's asking you for mean power, this is how you can navigate weird questions like this. To go to the end of this video, I'm going to look at two questions now. See, these are a lot of application, right? It's like all kind of pattern also got. We're going to look at two questions about light bulbs, because light bulbs play an important role in circuits lah, okay? They're pretty, they light up, and people like to use them in basic circuits. Okay, so what do we have here? This is on page 16. MCQ question. Wow, did my pen just change color halfway? That's interesting. We have two lamps in series to a power supply. One lamp is this, one lamp is this. Huh? Well, when you see a circuit question that has no picture, you better draw it out. So try our best to draw it out. In series, power supply. So power supply, you can draw like that, lor. Two dots. Then go to two lamps. So lamp, you can use the X. And then another X. And then go back to power supply. So power supply here is how much? 250 volts. Wow! That's like the house switch the plug there, you touch there, that is 240 volts already. Okay. And then we have one lamp here. Let's label it. 240 volt. That's the rating. And 60 watt. The other one is 10 volt rated and 2.5 watt. Which statement most accurately describe what happened? Both lamp at normal brightness, light normally. Only one lamp will light, the other lamp will explode. Huh? How to know? Okay, this one can be kind of hard if you're not sure how to think about light bulbs. Firstly, the question is, what is this rating? 240, 60 watt, 10 volt, 2.5 watt. What does that mean? Well, that means this first bulb here, if you give it 240 volts, it will give out 60 watt of power. 60 watt power means what? Okay. Pause there a bit. Now, if you have a torchlight or your phone light or this kind of like baby light bulb here, this one you will play a lot in labs when you come and do labs. Okay? Really, really tiny little fella here. Anyway, this little fella on light bulbs, you can look on the body of it and just try to see what is the rating, the power rating. So here it says, I can barely see, but about 2 to 3 watts, 6 volts. So it means if you feed it 6 volts, it will give out 4 volts, 2 to 3 volts, 2 to 3 watts of power. Okay. If you have bigger light bulbs in your house, I plugged this from the chandelier just now. Can see it now. Okay. The camera's kind of glitching out, but yeah, this is your good old light bulb. Okay. This one, if I look really closely, I would see it's about 40 watts at 240 volts. So that's the rating. You feed it 240 volts somewhere there, it will give out 40 watts of brightness. More watts generally mean brighter bulb. More power come out, more energy, more powerful. Okay? Except for weird ones like this. This is the LED bulb. Have you seen this white color one in your rooms or somewhere? Now this one is, how many watt? 18 watt only, but it's very bright. Very efficient, this one. They don't lose energy because of heat. Anyway, so those are light bulbs. These are what we call ratings, power ratings. If you go above their rating, there's a chance you might make the bulb explode because they're not meant to take such a high voltage. Okay? If you give them a potential difference lesser than what they like, so like this one, if you give less than 240 volt, then it won't be as bright as 60 watt, it will be lesser. So this kind of tell you how bright is it. So let's see here. Let's go through each statement so we can see one by one. First one, both lamps light at less than their normal brightness. What is normal brightness? Normal brightness is, you give it 240, is 60 watt. That is the normal brightness. So is it getting 240 volts? Well, you can check and see. Supply is 250 volt. So here very ngam, just nice, here will drop 240. And then here can drop 10 volts. Just nice, oh. You feed them what they like. So they will light normally. So actually this is not correct. You 240, the fella like 240, so okay lor. Give this one 10, the fella like 10, okay lor. So no problem lah. It's not gonna be dimmer. It'll be just nice. So both lamps light normally. That sounds correct. Okay, put a check mark there first. Let's look at the other option first. Only the 60 watt lamp will light up. Sounds a bit not right. Why? Firstly, you connect two bulbs in series, right? Got current will flow, 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 flow. So there's current flowing through everywhere, and there's potential difference. So cannot be one lamp only light ma. Both lamp will light up. Okay, sure. So that is wrong. The last one, the 10 volt lamp will blow. Some people may say, oh miss, you connect to the supply or 250 or more than this 10 or so blow already lah, explode. No. 250 is the whole circuit's potential difference. The first bulb already take a drop of 240. So this one take 10 only. So just nice lah. So it's not going to explode. So D is not correct. So B is the one that will best describe this scenario. Okay, so you kind of have to think of the bulbs. You need to understand what the rating means, things like that. If you go above their rating, there's a chance they will explode. If you're below, they will light up, but not as bright. They'll be dimmer. Let's look at a kind of a mini past year question in paper 2 about light bulbs. Now this one's on page 69. We'll only do the first part lah. So the other parts, we're going to save it for later. You can try out part B, but the topic comes later. Okay, so we have bulbs in parallel now. Oh, these are usually how all those pretty lights in the mall, I don't know what they are called, Christmas lights, decoration lights, there's like a whole bunch of them, many colors one. Oftentimes they're connected in parallel. Anyway, what do we have here? We have a 12 volt battery with internal resistance. Oh, internal resistance has struck again. Connected to two identical filament lamps, L1, L2. And they have two switch, S1, S2. The power rating of each lamp is 48 watts for a potential difference of 12 volts. This is power rating. This means, like I mentioned earlier, when you test it in the factory, if you give it 12 volts, it will dissipate a power of 48 watts. And that is the rating law. That's recommended what you should give to it. Now, S1 is closed and S2 is open. State and explain whether the power transformed in the first light is 48 watts or not. Take about 3 minutes to think through this one and see how would you describe this. You can use your own words. It's okay, don't worry. Just try it out first. Pause the video and then try to see how to best think about this thing, how to describe it in a sentence. Okay. Well, some of you may be thinking how to describe. Well, there's a lot of describe kind of questions in circuits. They love to ask you to describe the effect of this, state and explain. So anyway, we have two things here. We have state and explain. Ooh, two command words. So we need to state yes or no, power transform, and then you need to explain why you said yes or no. So the question is, will this light bulb, when you close this switch, close it, will it give out 48 watts of power? Power rating 48 should give out 48, right? That depends on the potential difference across the light. So from here to here. What is the potential difference? The second bulb pretty much is ignored because its switch is open. So don't care about that one. So how the best way you can talk about this is the power transform 48 watts? The answer is no. Why? Because then you must explain. So you must state and explain all. That's what I mean. Because why? Because you want to talk about, is this V here 12 volts or not? You may say, yeah lah, miss lah, here 12 volts ma. Don't forget, you have lost volts here also. So your internal resistance of the battery will also waste some volts. So in the end, what actually comes down here to the light is not 12 volt anymore already. Yeah. So you want to talk about the internal resistance thing. So you can say, no, because your, wrong color, internal resistance of the battery, or you can just say internal resistance, causes some lost volts. So therefore, you say your potential difference across the terminal or across the bulb, in this case it's still the same, is less than 12 volts. And you won't dissipate 48 watts anymore. And power less than 48 watts. There we go. So that's two ideas. First comes from your no, and then your because is all this explanation. So 2 marks there, just for explaining. It's a B1 and a B1 there. Okay, so just remember, whenever you see this rating, you say if the potential across the light is 12 volts, then yes, it will give out 48 watts. Okay, they already calculated in the factory, they test the rating already. Okay, so that's how you can think of bulbs. All kinds of interesting bulbs, series, parallel, you'll see more of them, don't worry. So that's the main idea of power, energy being transformed. Just remember, whenever the charge flows through a component, it will give the component energy, and the component will throw the energy out as light or heat or some other stuff. That's the whole idea. In the next bonus video, it's going to be a short one. Well, it's going to be a bonus extra one. But I'm going to talk about the reasoning why. Just now I mentioned very briefly, like maximum power and the graph, the weird shape graph. We're going to look more into that and 2 example questions from that thing. So I'll see you in the next bonus video about power, maximum power.